third installment of this dynamics topic, I'm going to be looking at equilibrium, one-dimensional and two simple dimensional contexts. I'll be looking at algebra addition, vector addition, and vector addition by resolution in components. Now, if you haven't checked out my Kinematics playlist, please do so because I've discussed so many things about vectors and scalars, how to do vector addition and subtraction. So check out that playlist on Kinematics. I've also done two previous videos to this dynamics video here, which are labeled A and B. Now these are going to be labeled C and D because we're going to be mixing a bit of the concepts in my following video in this earlier video. So if that makes sense, let's get started. So force is a vector quantity and therefore needs a direction. Okay, so we need to give it our direction. And in looking at vectors, our length and direction in a vector diagram basically tells us those two things. Now, force is measured in newtons. Forces can be resolved in two perpendicular components in the x and y directions. By using these two perpendicular components, you can determine the equilibrium of a system and the net force acting on the system. So let's have a look. We've got a few questions here and we're going to be looking at vector addition. So firstly, vector addition, we're going to be looking at a scenario where we're going to arrange P, Q and R in a specific order by those questions. So let's have a look here at P plus Q plus R. So firstly, I've drawn the arrows to scale and you can see that the blue is P, Q is green and R is red, and the resultant will be black. So you can see that I've arranged them P going east, Q going west and R going west, and you'll get a 7 Newton west answer for the first one. Okay, so if you draw these to scale, you will get the right answer as long as you put in the right orientation. Now let's have a look here at the next question, which is P minus Q plus R. So if you look firstly, I've placed down P, same as our first video. So P is going 7 newtons to the east. However, Q is going to be flipped because it's a minus value. So we're going to flip Q in the same direction as P. R stays the same value because we're just adding R. So your answer will be 11 newtons to the east. Okay, so you can see that by the black resultant. We're going to do P minus Q minus R. And you can see that I've put P in the same direction as always. I've flipped Q because it's a minus value, so flip it to go east. And the same for R. Now you'll see here we have 21 newtons east, which is the final answer. Okay, so you can see that there I've used different colors to represent the different arrows. If you draw them to scale, you will get a good answer as long as you put it in the correct orientation. So let's have a look here now at my next question, and this is one that we've discussed in class at length. It is a difficult question. I'm not going to lie there. So let's have a look at the mathematics. Now, it's a very difficult question because there's a few things at play. So you've got here, let's read it. So X and Y are connected by separate strings over two pulleys of a 15 kilo mass, as shown in the diagram. The system of three masses is in static equilibrium. Now that's important for us to work out the mathematics later on because static equilibrium just means that it's zero as net forces on the Fx and the Fy axis. So assuming the pulleys in the system are frictionless and weightless, find the values of X and Y. Now I first split up this into horizontal and vertical components. So if you look here, we've got T1x plus T2x plus T3x. And now substituted T1x, T2x and T3x by the values above that I found each of those corresponding vectors. So once you substitute the correct values where T2x and T3x is, you'll see you get T2 cos 25 plus T3 cos 45 because we're dealing on the horizontal axis. Now our Fx net is 0 because it's static equilibrium. Okay, now you just need to do simple algebra and move T2 cos 25 on one side and leave the T3 cos 45. Now if you want to make T2 or T3 the subject, you just need to divide each side by the cos angle. Okay, now let's have a look here at the vertical axis. So I've split this up into two different slides on my PowerPoint, and I've looked to find the answer for X first. So I found the net force acting on that 15 kilo block, which was 147 newtons. So I divide 15 by 9.8 and I got 147. Now the T2 sine 25 and the T3 sine 45 came from the previous slide when I worked out each of those vectors. Now basically substituting T3 from our previous slide into this equation here, we can see cos 25 divided by cos 45, T2 times sine 45. Now to resolve that, you get an answer of 1.282. Now that brings it forward into a lot simpler terms, because you can just times sine 45 to that answer and you'll get T2 as 0.907. Add that to sine 25 and you get T2 as 1.329. Now divide that onto the 147 side so we can find T2, and T2 comes to 110.61 newtons. Now we want it in kilos, so you divide by 9.8 and you get T2 as 11.287 kilos for X. It's a mouthful, it's very difficult, and I'm asking my students to copy this down before we tackle it in class with another problem in our homework sheets. So let's have a look here at, we're going to find now Y. So you got 147 is the same, so that was just 15 kilos divided by 9.8. I've inserted the variables that we found in our previous two slides. Now I've inserted where T2 is, cos 45 divided by cos 25, and this will give us T3 as 0.780. Now times it by sine 25, and then you get T3 as 0.33. Add sine 45 to that, and you get T3 as 1.037. Now divide it move that side to the 147 and you'll get 141.77 newtons. Now to work that out into kilos, just divide by 9.8 meters per second and you'll get T3 or Y as 14.467 kilos. That's a very difficult question, and it does take a lot of knowledge and skill to tackle these static equilibrium pulley questions. Okay, so let's have a look at another question in class that we've looked at extensively, and this is when we have mass being pulled by a certain angle and working out the tension or the force on a string. So we've got here a mass of 32 kilos hangs on a string which is pulled on a side by a force until the string makes an angle of 30 degrees to the vertical. What is the force pulling the support to the string on the string side, and what is the tension in the rope? So basically, to find the angle, we got Fx equals Fx times 10 of the angle. Sorry, I apologize. And you get 250 equals 60 times 9.8 times 10 of the angle. Move the 60 times 9.8 meters per second on the left hand side. That answer, and you'll get 23 degrees. Now for B, for the tension of the string, it is force divided by cos of the angle. 60 times 9.8, which is what we used earlier, divided by cos 23, and you get 638.8 newtons. Okay, so let's have a look at the final question here. Now we've got a mass hanging by two different tensions of a string, and you can see here that they created an angle. Now I moved the vectors accordingly to how they arrange themselves in a triangle, and you can see on my diagram that 110 is the difference between 70 and 180 degrees on the left hand side. And then you've got here 60 degrees. Now that 60 degrees is not inside that triangle. We've found that it has to be 40. Now the reason why it is 40 is basically because the 70 and the 20 above the 40, then the 20 gets minus by the 60, and you'll get 40 degrees as the angle. Okay, now because all triangles equal 180 degrees, you do 110 plus 40 will give you 30 degrees. Now using the sine rule, A divided by sine A equals B sine B. You basically arrange those numbers in according order and just cross multiply where it counts, and you'll get T1 as 304.8 newtons and T2 as 573.1 newtons. Thank you for watching. I'm going to do many more videos in dynamics. I hopefully explained it with enough detail, and I've taken enough videos and screenshots with exam style questions there to support you in class. If you haven't already, and I've said this many times, please subscribe, like, dislike. Any feedback is wonderful for me to produce my next set of videos. So thank you for your support.